Swayam Prabha. Digital India. Educated India.
Now let us go to discuss the continuation of prediction, the posterior prediction. We have an equations of p of y star of bar by x into y comma x star of integral p of y star bar x star of theta of p of theta by x y d theta is equation 9.37. We computed the prediction distribution of y star at the test input x star using the parameter prior p of theta. In principle, the predicting with the parameter posterior p of theta by x comma y is not a fundamental difference, given that in our conjugate model the prior and the posterior are both Gaussian. Therefore, by following the same reasoning as in the previous section, we obtained the posterior prediction distribution. So, probability of y by x comma y comma x star is equal to integral p of y star by x star comma theta of p of theta by x comma y d theta. Then the integral n of y star by phi transpose of x star theta comma sigma square of n of theta by mn comma sn d theta. So, after integration we have n of y star by phi transpose of x star mn and phi transpose x star sn of phi of x star plus sigma square is 57c says that. Therefore, expectation of y star by x equal to y comma x star is equal to phi transpose of x star mn equal to phi transpose of x star of theta map. So, the term phi transpose of x star into Sn of phi of x star reflects the posterior uncertainty associated with the parameter theta. Note that Sn depends on the training inputs through phi. So, the predictive meaning phi transpose of x star mn coincide with the prediction made with the map estimate of theta map. So, we have a note, the marginal likelihood and the posterior prediction distribution by replacing the integral a 57a. So, the predictive distribution can be equivalently written as the E theta of bar x comma y of p of y star by x star theta, where the expectation is taken with respect to the parameter of posterior of p of theta by x comma y. So, writing the posterior prediction distribution in this way highlights a close resemblance to the marginal likelihood. So, the key difference between the marginal likelihood and the posterior prediction distribution are: number one, the marginal likelihood can be thought of predicting the training targets y and not the test target y star. So, the marginal likelihood averages with respect to the parameter prior and not the parameter posterior. So, we have a note, and the mean and the variance of noise free function values. In many cases, we are not interested in the predictive distribution p of y star by x comma y of x star of the noisy observation y star. Instead, we would like to obtain the distribution of the noise free function values f of x star equal to phi transpose of x star theta. So, we determine the corresponding moments by exploiting the properties of means and variance, which yields E of f of x star by x comma y equal to E theta of phi transpose of x star theta by x comma y equal to phi transpose of x star into E theta of theta by x comma y. So, we have phi transpose of x star mn equal to mn transpose of phi of x star. This implies V theta of f of x by x comma y equal to V theta of phi transpose x star theta by x comma y. Therefore, phi transpose of x star V theta of theta by x comma y equal to phi of x star, which is equal to phi transpose of x star Sn of phi of x star. So, that equation represent as expectation and variance of the noisy free functions represented 58 and 59, and the predictive mean is the same as the predictive mean for the noise observation, and noise has a mean 0 and predictive variance is sigma square, which is the variance of measurement noise. When we predict noisy function values, we need to include sigma square as a source of the uncertainty, but this term is not needed for the noisy free prediction. Here the only remaining uncertainty terms from the parameter posterior. So, note distribution over function, the fact that we integrate out the parameters theta induces the distribution over functions. So, if we sample the theta is approximately p of theta by x comma y from the parameter posterior. So, we obtained a single function realization of phi transpose of phi of dot, this mean the function mean function. So, the set of all expected function value is e theta of f of dot by theta comma x comma y of this distribution over function is mn transpose of phi of dot. So, this is a marginal variance, that is the variance of the function f of dot is given by phi transpose dot of Sn of phi of dot. So, for example, the posterior over function, let us revisit the Bayesian linear regression problem with a polynomial of degree 5. So, we choose the parameter prior p of theta equal to n of 0 comma 1 by 4 I. This figure 9.9 visualize the prior over function induced by the parameter prior and a sample function from this prior. So, this figure 9.10 shows that the posterior over function that we obtain the Bayesian linear regression. So, the data set shows that number 1 a panel of the training set training the data, and then the Bayesian linear regression and the posterior over function of the training data. Number 2 shows that posterior distribution over function include the function we would obtain through maximum likelihood and MAP estimation. So, the posterior over function represents the marginal uncertainties that is shaded, showing the 67% and 95% prediction confidence bounds of MLE, that is maximum likelihood, and a MAP estimate. So, later of which is identical to posterior mean function. So, the function we obtain using map estimate also correspond to the posterior mean function in the Bayesian linear regression setting, and here C stands for samples from the posterior over function, shows some plausible realization of function under the posterior over functions which are induced by the samples from the parameter of the posterior. And figure 9.11 shows that some more posterior distribution over function induced by the parameter posterior, and this is 9.11. shows some posterior distribution over function induced by the parameter posterior for a different polynomial degree m. So, the left panel shows the maximum likelihood function theta transpose ml of phi of dot. The map function is theta transpose map of phi of dot, which is identical to the posterior mean function, and the 67% and 95% predictive confidence bounds obtaining by Bayesian linear regression are represented by the shaded areas. So, the right panel shows the samples from the posterior over function. Here we sampled parameter theta I from the parameter posterior and computed the function phi transpose of x star of phi theta I, which is a single realization of the function under the posterior distribution over functions. For low order polynomial, the parameter posterior does not allow the parameter to vary much. The sampled function are nearly identical. When we make the model more flexible by adding more parameters, that is, we end up with a higher order polynomial. These parameters are not sufficiently constrained by the posterior, and the sample function can be easily visualized, visually separated. So, we also see in the corresponding panels on the left how the uncertainty increases, especially at the boundaries. So, although for the 7th order polynomial the map estimate yields a reasonable fit, the Bayesian linear regression model additionally tells us that the posterior uncertainty is huge. So, this information can be critically when we use this prediction in a decision making system, where bad decision can have a significant consequences. Example in reinforcement learning or robotics is a Bayesian linear regression explained here. And here the orange is a map and the cement color is BLR, Bayesian linear regression, and then the light blue MLE, and similarly we have a the variation with the decision regarding that the linear regression. So, this is the reinforcement learning or robotics. Now, we have a graph corresponding to the mapping where m equal to 3 for first figure. Posterior distribution for polynomial of degree m equal to 3 is a left, and sample from the posterior over the function is a right, and B is a posterior distribution for polynomial of degree m equal to 5 is a left, and samples from the posterior over function is a right. And C the picture shows that m equal to 7 is a left, and distribution of the polynomial of degree and sample from the posterior over the function is a right, and 65% to 95% the confidence limit, get it. Now, we have another topic is computing the marginal likelihood. So, the section we highlighted the importance of marginal likelihood for Bayesian model selection. In the following, we compute the marginal likelihood for the Bayesian linear regression with conjugate Gaussian prior on the parameters. That is exactly the setting we have been discussing in this chapter. Just to recap, we consider the following generative process. Theta is approximately n of m naught comma s naught 60a, and yn divide xn comma theta is approximately equivalent to n of xn transpose theta gamma sigma square is 60b represent, where n equal to 1 to n. Therefore, the marginal likelihood is given by p of y by x is equal to integral p of y by x comma theta of p of theta d theta which is equal to integral n of y by x naught comma sigma square I into n of theta by m naught comma s naught into d theta. So, where we integrate out the model parameter theta. So, we compute the marginal likelihood in two steps. First, we show that the marginal likelihood is a Gaussian. Second, we compute the mean and covariance of the Gaussian. So, the marginal likelihood is Gaussian. From this section, we know that the product of two Gaussian random variable is unnormalized Gaussian distribution. And number 2, the linear transformation of a Gaussian random variable is Gaussian distributed. And the equation 61b require the linear transformation to bring n of y by x naught comma sigma square I into the form of n of theta by mu comma summation for some mu and sigma. Once this is done, the integral can be solved in closed form. So, result is a normalizing constant of the product of the two Gaussian. So, the normalizing Gaussian itself has a Gaussian shape. See 76 equation. And then the mean and covariance, we compute the mean and covariance matrix for the marginal likelihood by exploiting the standard result for means and covariance of affine transformation of random variable. And we have to see that section. The mean of the marginal likelihood is computed by expectation of y over x equal to E expectation of theta comma epsilon of x theta plus epsilon, which is equal to x into E of theta, which is equal to x into m naught. So, epsilon is approximately equal to n of 0 comma sigma square I is a vector of IID random variable. So, the covariance is given by covariance of y by x equal to covariance of x theta plus epsilon base theta comma epsilon equal to covariance of x theta base theta plus sigma square I. And it's for simplification x k, take it outside, covariance of theta x transpose plus sigma square I. So, x into covariance of theta is represent x into s naught x transpose plus sigma square I. Hence, the marginal likelihood is p of y by y over x equal to 2 pi whole power minus n by 2 determinant of x naught x transpose plus sigma square I into whole power minus half into expectation of minus half into y minus x into m naught transpose into x s naught x transpose plus sigma I whole inverse into y minus x m naught. And this figure shows that a geometric interpretation of linear squares. First one represent the noisy observation of the yn represent the blue of the function, and the corresponding f of x1 is output of the location of xn using the data set. And based on the picture B is the maximum likelihood solution interpreted as a projection. So, here orange dots are the projection of the noisy observation, and a blue dot onto the line theta mlx, and the maximum likelihood solution to the linear regression problem find the subspace onto the which the overall projection error orange lines of the observations is minimized. Therefore, n of y by x m naught comma x s naught x transpose plus sigma square I, and given the close connection with the posterior prediction distribution. So, the remark on the marginal likelihood and posterior prediction distribution earlier in this section. So, the functional form of the marginal likelihood should not be too surprising. Next, maximum likelihood as an orthogonal projection. Having crunched through much algebra to derive maximum likelihood and map estimates, we will now provide a geometric interpretation of maximum likelihood estimation. So, let us consider a simple linear regression setting y equal to x theta plus epsilon where epsilon is approximately n of 0 comma sigma square, in which we consider linear function f such that r to r that go through the origin. We omit the future here for clarity. So, the parameter theta determines the slope of the line, and figure 9.12a shows the one dimensional data set. 12a is a one dimensional data set of A, and with training data of x1 y1, x2 y2 and so on xn y1, we recall the results from 9.21 and obtain the maximum likelihood estimator for the slope parameter as theta ml equal to x transpose x whole inverse into x transpose y equal to x transpose y by x transpose into x belongs to R, where x equal to x1, x2 and so on xn of the transpose in R power n, and y equal to y1, y2, yn transpose belongs to R power n. So, this means for the training input x, we obtain the optimal reconstruction of the training target as x suffix theta ml equal to x into x transpose y by x transpose x equal to xx transpose y by x transpose x. So, we obtain the approximation with minimum least square error between y and x theta. So, in the general linear regression case where y equal to theta phi transpose of x theta plus epsilon, where epsilon is approximately n of 0 comma sigma square. So, with the vector valued futures phi of x in R power k, so we can interpret the maximum likelihood result y is approximately phi of theta ml, and theta ml is phi transpose phi whole inverse into phi transpose y. So, as a projection onto a k dimensional subspace of R power n, which is spanned by the column of the future matrix. So, if the future function phi k that we use to construct the future matrix phi are orthogonal or orthonormal, so we obtain the special case where the column phi form an orthogonal basis such that phi transpose phi equal to I. So, this will lead to the projection phi into phi transpose phi whole inverse into phi transpose y equal to phi transpose y equal to summation k equal to 1 to k phi k into phi k transpose y. So, that the maximum likelihood projection is simply the sum of the projection of y onto the individual basis vector phi k, that is the column of phi. Furthermore, the coupling between the different futures has disappeared due to the orthogonality of the basis, and many popular basis function in signal processing such as a wavelet and Fourier's basis are orthogonal basis functions. So, when the basis is not orthogonal, one can convert a set of linear independent basis function to an orthogonal basis by using Gram-Smith orthogonalization process. So, based on this component, we have to go to the dimensionality reduction with the principal component analysis. So, in this talk we will discuss the principal component analysis and algorithm for linear dimensionality reduction. So, the principal component analysis proposed Pearson in the year of 1901 and Hotelling 1933 has been around for more than 100 years and is still one of the most commonly used techniques for data compression and data visualization. So, it is also used for the identification of simple patterns, latent factors and structures of high dimensional data. So, in the figure we have a data set of with x1 and x2 coordinate, and this illustrates the dimensionality reduction of the original data set and does not vary much along the x2 direction, and B represent the data from A and can be represented using the x1 coordinate along with nearly no loss. So, this data is compressed data where only the x1 coordinate is relevant. So, that is the meaning of the picture 1 A and B represent the dimensionality reduction, and this is signal processing community PCA is also known as Karuhan-Loewi transform. So, in this talk we derived a PCA principal component analysis from first principles, drawing on our understanding of basis and basis changes like projection, eigenvalues, Gaussian distribution and constraint optimization. So, these are all included in this PCA. Now, we have to set a problem. More concretely, we consider IID data set X equal to n data independent ideas of R power D with the mean 0 that possesses the data covariance matrices. So, S equal to 1 by n into xn transpose, n varies from 1 to n. Further, we assume that there exists a low dimensional compressed representation Zn equal to B transpose xn belongs to R power n of xn, where we define the projection matrix B equal to B1, B2 and so on Bm in R power D cross m. So, we assume that the column B are orthonormal, so that B transpose Bj equal to 0 if and only if I not equal to j, and Bi transpose into Bi equal to 1, we seek an m dimensional subspace U is subset of R power D, and dimension of U equal to m which is less than D onto which we project the data. So, we denote the projected data by xn in U and their coordinates to the basis vector B1 to Bm of U by Zn. So, our aim is to find the projection of xn in R power D, or equivalently the code Zn and the basis vectors B1 to Bm, so that they are as similar to the original data xn and minimize the loss due to the compression. So, this is the map. Originally R power D x domain is given and compressed with R power m of z and reconstructed in x bar. So, R square is a 2 dimensional effect with a canonical basis E1 required 1 comma 0 and E2 required 0 comma 1 are the two bases, and from the domain we have to send it, and then we have to generate with E1 E2 of the linear combination. So, we can do with the linear combination from domain to codomain and represent the eigen vectors, say phi comma 3 equal to phi E1 plus 3 E2. Now, we consider the vectors of the form x bar equal to 0 comma z in R square, where z in R. So, they can always be written as 0 E1 plus z E2. This represents the vector. It is sufficient to remember or store the coordinate or code of z of x bar with respect to E2 vectors. More precisely, the set x bar vector forms a vector subspace dimension of u equal to 1, and because u span with E2. So, this figure illustrates the setting with consider the principal common analysis, where Z represents the lower dimensional representation of compressed data x bar and plays the role of a bottleneck which controls how much information can flow between x and x bar. In PCA, we consider a linear relationship between the original data x and its lower dimensional code Z, so that Z equal to B transpose x and x bar is equal to Bz for a suitable matrix B. Based on the motivation of thinking of a PCA as the data compression technique, so we can interpret the arrow in the figure as a pair of operation representing encoder and decoders. So, the linear mapping represented by B can be thought of the decoder, which map the low dimensional code Z in R power m of m tuple back into the original data space R power D. Similarly, B transpose can thought of the encoder and which encodes the original data x as the low dimensional compressed code Z. So, this is the picture corresponding that our handwriting digits from MINST data, and this will use in the data set, and which contains 6000 examples of handwritten digit 0 to 9. So, each digit is a grayscale image of a size 28 cross 28, So, it consists of 784 pixels, so that we can interpret every image in this data set as a vector, and this is the digit shown in the figure. And next we have a maximum variance perspective. So, the figure 10.1 gave an example of how a two-dimensional data set can be represented using a single coordinate, and 10.1b. So, this is a 10.1b, 1a is here, this is a 10.1a and 1b, how the linear is converting, and this can be illustrated in terms of the dimensional reduction, and this will be useful here to choose the maximum variance. So, we choose to ignore the x2 coordinate of the data because it did not add too much information, so that the compression data is similar to the original data in the figure. So, we could have chosen to ignore the x1 coordinate, but then the compressed data had been very dissimilar from the original data, and much information in the data would have been lost. So, if we interpret the information content in the data as how the space filling, so the data set is, then we can describe the information contained in the data by looking at the spread of the data. So, we know that the variance is an indicator of the spread of the data, and we can derive principal component analysis as the dimensionality reduction algorithm that maximize the variance in the low dimensional representation of the data to retain as much information as possible. That is, figure 10.4 illustrate this. Now, considering the setting a discussion of this, our aim is to find the matrix B that retain as much information as possible. When compression the data by projecting it onto the subspace spanned by the column B1 to Bm of B, retaining most information after data compression equivalent to capturing the largest amount of variance in the low dimensional code. So, refer Hoteling 1933, and we have a note related to centered data. For the data covariance matrix equation 10.1, we assumed that centered data we can make the assumption without loss of generality. Let us assume mu is the mean of the data. Now, we have the properties of variance, and discuss in this section we obtain variance of z equal to variance of B transpose of x minus mu, and splitted into this into variance of B transpose x minus B transpose of mu, and this value becomes 1, therefore, variance of x into B transpose of x only will come. So, variance of z equal to variance of B transpose x over the x. So, this means the lower dimensional subspace that maintain as much as variance when the blue dot is projected onto the subspace in the orange, right, and then connected with a yellow line. So, the variance of the low dimensional code does not depend on the mean of the data. Therefore, we assume that without loss of generality that the data as a mean is 0, and with the assumption that mean of the low dimensional code is also 0. Therefore, expectation of z equal to expectation of B transpose x equal to B transpose of expectation of x, which is equal to 0. So, this way we can incorporate it corresponding to the picture of the linear of the lower dimensional subspace using the principal component analysis. So, we maximize the variance of the low dimensional code using the sequential approach. Now, we start the single vector B1 in R power D that to maximize the variance of the projected data. So, we aim to maximize the variance of the first coordinate Z1 of Z in R power n, so that V1 equal to V of Z1 equal to 1 by n into summation n equal to 1 to n Zn square is maximized. We exploited the IID assumption of the data and defined Z suffix 1 n as the first coordinate of the low dimensional representation of Zn in R power n of xn. Note that first component of Z1 is given by Z1n equal to B1 transpose xn. So, it is the coordinate of orthogonal projection of x1 onto the one dimensional subspace spanned by B1. Therefore, which yield V1 equal to 1 by n into summation n equal to 1 to n B1 transpose xn the whole square equal to 1 by n summation n equal to 1 B1 transpose into xn transpose B1. So, therefore, B1 transpose equal to B1 transpose of 1 by n into summation n equal to 1 to n xn transpose into B1. So, which is equal to this value is SB1. Therefore, B1 transpose into SB1 will come, and where S is the data covariance matrix and equation defined in 1, and in point 9a we have used the fact that dot product of the two vectors is symmetric with respect to its argument. So, B transpose xn equal to xn transpose Bn. So, we notice that the arbitrarily increasing the magnitude of the vector B1 increases V1, that is a vector B1 that is 2 times longer can result in V1, that is the potentiality of 4 times larger. Therefore, we restrict all solution to norm of B1 square equal to 1, which results the constraint optimization problem, in which we seek the direction along which the data varies most. So, with the restriction of the solution space to unit vectors, the vector B1 that points in the direction of maximum variance can be found by the optimization problem maximize of B1 transpose SB1 subject to norm of B1 square equal to 1. So, we obtain the Lagrange's method L of B1 lambda equal to B1 transpose SB1 plus lambda 1 of 1 minus B1 transpose into B1 to solve the constraint is optimized problem, and the partial derivatives of L with respect to B1 and lambda 1 are dou L by dou B1 equal to 2 B1 transpose S minus 2 lambda 1 B1 transpose, and dou L by dou lambda 1 equal to 1 minus B1 transpose B1 respectively. Setting these partial derivative to 0, therefore, this SB1 into lambda 1 B1 will come. For this case, we have B1 transpose equal to 1. By comparing with the definition of eigenvalue decomposition, we see that B1 is eigenvector of the data covariance matrix S, and the Lagrange's multipliers lambda 1 plays the role of the corresponding eigenvalue. Therefore, eigen property allows to rewrite our variance objective as V1 equal to B1 transpose SB1 equal to lambda 1 B1 transpose B1, which is equal to S1 lambda 1, because from 13 we have what SB1 equal to lambda 1 B1 and substitute it, and this 1 replace 1 equal to B1 transpose to B1, so that B1 transpose SB1 equal to lambda 1 B1 transpose B1, which is equal to 1, which is equal to lambda 1. Therefore, V1 equal to lambda 1. So, that is the variance of the data projected onto the one dimensional subspace equals the eigenvalue that is associated with the basis vector B1 that spans this subspace. Therefore, to maximize the variance of the low dimensional code, we choose the basis vector associated with the largest eigenvalue of the data covariance matrix. So, this eigenvector is called a first principal component. So, we can determine the effect or contribution of the principal component B1 is a original data space by mapping the coordinate Z1n back to data space, which gives us a projected data point xn bar equal to B1 to Z1 equal to B1 transpose xn in R power D in the original data space. So, note, although xn bar is a d-dimensional vector, it only requires a single coordinate Z1n to represent it with respect to the basis vector B1 in R power D. So, taking all the digit 8 in the M1 IST training data, we compute the eigenvalues of the data covariance matrix. In figure 10.5a shows the 200 largest eigenvalues of data covariance matrix, and we see that only a few of them have a value that differs significantly from 0. Therefore, most of the variance when projecting data onto the subspace spanned by the corresponding eigenvectors is captured by only a few principal components as shown in the figure 10.5b. Next, we have a m dimensional subspace with a maximal variance. Assume we have found with first m minus 1 principal components as m minus 1 eigenvectors of S that are associated with the largest m minus 1 eigenvalues. Since S is symmetric, so the spectral theorem states that we can use these eigenvectors to construct orthonormal eigenbasis of an m minus 1 dimensional subspace of R power d. So, generally the mth principal component can be found by subtracting the effect of the first m minus 1 principal component b1 to b suffix m minus 1 from the data, thereby trying to find the principal component that compress the remaining information. So, we then arrive at the new data matrix. So, x bar equal to x minus summation I equal to 1 to m minus 1 bi transpose x equal to x minus b suffix m minus 1 x. So, call it as 17. So, x varies from x1 to xn in R power d cross n contains the data points as a column vector, and b suffix m minus 1 equal to summation I equal to m minus 1 into bi transpose is a projection matrix that project onto the subspace spanned by b1 to bm minus 1. So, note throughout this chapter talk we do not follow the convention of collecting data as the rows of the data matrix, but we define them to the column of x. This means that our data matrix x is a d cross n matrix instead of the conventional n cross d matrix. The reason for our choice is that the algebra operation work out smoothly without the need to either transpose the matrix or to redefine the vector as a row vector that are left multiplied onto the matrices. So, to find the mth principal component, so we maximize the variance Vm equal to V of Zm equal to 1 by m into 1 by n into summation n equal to 1 to n Z suffix mn square equal to 1 by n into summation n equal to 1 to n Bm transpose of xn whole square equal to Bm transpose Sbn subject to norm of Bm square equal to 1, where we followed the same steps as in the 9b and define S as the data covariance matrix of the transformed data set. As previously, when we looked at the first principal component alone, we solved the constraint optimization problem and discovered the optimal solution of Bm is the eigenvector of S that is associated with the largest eigenvalues of S bar. So, overall to find m dimensional subspace of R per D that remains as much information as possible. So, the PCA tells us to choose the column of the matrix B as the m eigenvectors of the data covariance matrix S that are associated with the m largest eigenvalues. So, the maximum amount of the variance PCA can capture with the first m principal component is Bm equal to summation m equal to 1 to m lambda m. So, it turns out that Bm is also a eigenvector of S. More generally, the sets eigenvectors of S and S bar are identical. Since both S and S bar are symmetric, we can find a ONB of eigenvectors using the spectral theorem. So, there exists a D distinct eigenvectors for both S and S bar, and next we show that every eigenvectors of S is an eigenvector of S bar, and also assume we have already found the eigenvectors b1 to bm minus 1 of S. So, the eigenvector bi of S, Sbi equal to lambda I bi. So, S bar bi equal to 1 by n into xx bar transpose bi, which is equal to 1 by n into x minus bm minus 1 x into x minus bm minus 1 x whole transpose into bi. So, simplify and cross multiply these two, we have S minus S b m minus 1 minus b m minus 1 s plus b m minus 1 s into b minus b suffix m minus 1 into bi. So, we have two distinct we distinguish between the two cases, that is I greater than equal to m and I less than m. If I greater than equal to m, Bi is the eigenvector that is not among the first m minus 1 principal component, then Bi is orthogonal to the first m minus 1 principal components, and B suffix m minus 1 into Bi equal to 0 if I is less than m, that is Bi is among the first m minus 1 principal component, then Bi is also a basic vector of the principal subspace onto which B suffix m minus 1 project. Since B1, B2 and so on, B suffix m minus 1 are ONB of the principal subspaces, so we have a what Bm minus 1 into Bi equal to Bi, therefore two cases can summarize. B suffix m minus 1 Bi equal to Bi if I is less than m, or B suffix m minus 1 into Bi equal to 0 if I is greater than equal to m. So, in the case I greater than equal to m and using equation 20 in 19b, we obtain S bar Bi equal to S minus Bm minus 1 into S into Bi, which is equal to Sbi equal to lambda I Bi, where Bi is also eigenvector of S with eigenvalues lambda I, and specifically Sbm equal to S bar Bm equal to Sbm equal to lambda m Bm. So, the equation 21 reveals that Bm is not only an eigenvector of S, but also S bar, and specifically lambda m is the largest eigenvalue of S bar and lambda m is the mth largest eigenvalues of S, and both have the associated with the eigenvector Bm. So, in this case I is less than m. By using 20 and 19b, we obtain S bar Bi equal to S minus Sbm minus 1 minus Bm minus S plus Bm minus 1 S into Bm minus 1 Bi equal to 0, which is equal to 0 Bi. This means B1 to B minus B suffix m minus 1 are also eigenvector of S bar, but they are associated with eigenvalues of 0, so that B1 to Bm minus 1 span the null space of S bar. So, where lambda m are the m largest eigenvalues of data covariance matrix S, consequently the variance lost by the data compression through principal component analysis Jm is equal to summation j equal to m plus 1 to d lambda j, which is equal to Vd minus Vm. So, instead of these absolute quantities, we can define the relative variance captured as Vm by Vd. So, the relative variance lost by the compression as 1 minus Vm by Vd. So, overall every eigenvectors of S is also an eigenvector of S bar. However, if the eigenvector of S are part of the n minus 1 dimensional principal subspaces, then associated with eigenvalue of S bar is 0. So, with this relation Bm dash into Bm equal to 1 and variance of the data projected onto the mth principal component is Bm equal to Bm transpose Sbm, and using 21 we have lambda m into Bm transpose into Bm equal to lambda m. So, this means the variance of the data when projected onto m dimensional subspace equals the sum of the eigenvalues that are associated with the corresponding eigenvectors of the data covariance matrix. So, this figure shows that the properties of training data of MNIST of 8 digits and eigenvalues sorted in the descending order, and maximum 500 captured the variances, and this picture A represent the eigenvalue of data covariance matrix of all digits in MNIST training set, and figure B represent the number of principal component versus captured variance. So, the variance captured by principal component picture deducted like this. So, the B actually shows that the corresponding eigenvalue sorted from domain to codomain of the variance, and here the down the figure represent the linearity already explained, and here the blue dot is original and it is orthogonal to one another, and this find the subspace that minimize the length of the difference vector between the projected orange and blue connected with the yellow line of the data of the eigenvalues of MNIST 8. So, taking all digit 8 in the MNIST training data, we compute the eigenvalues of data covariance matrix. So, the figure 10.5a shows that the 200 largest eigenvalues of data covariance matrix. The figure 10.5a shows the 200 largest eigenvalues of data covariance matrix. So, we see that only a few of them have the value that differs significantly from 0. Therefore, most of the variance when projecting data onto the subspace spanned by the corresponding eigenvector is captured by only a few principal component as shown in the figure. So, overall, to find m dimensional subspace of R per D that retain as much as information is possible. So, the PCA tells us to choose the column of the matrix B as the m eigenvectors of the data covariance matrix S that are associated with the m largest eigenvalues. So, the maximum amount of PCA can capture with the first m principal component is Vm equal to summation m equal to 1 to m lambda m, where lambda m are the m largest eigenvalues of data covariance matrix S. Consequently, the variance lost by the data compression through PCA is Jm equal to J varies from m plus 1 to d lambda j equal to Vd minus Vm. So, instead of these absolute quantities, we can define the relative variance captured by Vm by Vd. So, the relative variance lost by the compression is 1 minus Vm by Vd is a required answer.